And the majority of my presentation is basically going to be on this slide. So I thought this was a really cool graphic. It shows a lot of stuff of what's going on here. So as the Earth is moving around the sun, you'll notice a couple things. First, the orbit's not perfectly circular, so you have the sun a little bit offset. And on the top and bottom, you should have the equinox, where the tilt of the Earth is perfectly in line, so you have the equal time of day and night on the. And then on here you have the solstice, where you have like the longest day and the longest night. You have the longest night in the winter. And one kind of interesting thing is, over here when it's closest to the sun, the northern hemisphere, so you've got the Earth here, and it's tilted, so the Earth's like spinning the tilt. And if you have the sun over here, the sun is shining on the Earth, and most of it is hitting the lowest part of the Earth, where on the other side over here, you have the sun, and it's shining light, and you'll notice that most of it's hitting the top of the Earth. So when you have this Analemma pattern, the up and down motion here is due to the fact that the tilt, as it's going around the sun's hitting the different parts of the Earth. So this up and down motion is due to the sun kind of hitting the different parts of the Earth as the Earth rotates around the sun. So really, it's a really difficult
Do you understand what I'm
thing
saying?
to
So, yeah, it's gonna be,
Yeah.
it's,
So as over the course of the year, you'll see the sun moving up and down basically because of the tilt of the Earth.
But
But-
that's a picture at the same time every day? Over
The same
course of
exact
year?
time.
At the same exact time every day?
Same exact time.
Like noon?
Yeah.
Okay.
And then you have another motion which is back and forth here. And that's due to Kepler's second law, which is his laws of planetary motion. And that's this why it's not a perfect circle. It's like an ellipse. And because of that, you'll have like the sun here, and the Earth is orbiting, and I'll exaggerate it to make it like you can see it better. And you'll have the Earth will be moving around the orbit, and it'll take the same amount of time to move that distance as it does to move only that distance. And that's because when the Earth is moving around the sun, the sun's kind of like pulling it, and it's moving faster. So as it gets here, this Earth is moving faster around the sun, and due to that, you have like the sun, since you're taking the picture of the sun the same time every day, it'll be like a little bit late or a little bit early. So it'll be like, that's how you get the back and forth motion. So there's a combination of those two different things that gives you this pattern, but it gets a lot more complicated than that. Another thing I've noticed, I asked a couple like really smart people. You'll notice here that the times when you're supposed to have the equinox, which is like right here, is not exactly on the opposite side of the sun, which you would think it would be. And I'm not really sure why. We couldn't figure it out, short of emailing the guy that like actually created this graph. And
That's a really cool animation, and you know that the two sides are in sync. So when you see
yeah, so like here,
there, it matches that spot. You know, that's
And
really,
then-
really nice animation.
So and then like there is here, and then once it gets down to there, it'll be there. And that's what I'm saying, it's not like exactly opposite sides of the sun, which you would think it would be, because it's the same, you have the same length of day and night. And I couldn't figure that one out, but this also up here shows kind of what I was talking about. Like if the Earth wasn't tilted and you took a picture the same time every day, you wouldn't be getting this up and down motion. So you would actually just have a point in the sky rather than have this figure 8. You just have a point because it wouldn't be like it'd be the same around the equator. But if the Earth was perfectly circular and you had a tilt, you just get the back and forth motion. But if it was, no, actually you'd get this one. And if you had like an ellipse, it would get the other one. But it gets really complicated because I read several explanations of this. So like one guy, this guy's idea was like if you have an ant walking around the equator and then you have the sun, it's like moving up high. So if like the sun, I didn't like this guy's explanation though, explanation because the ant's like moving and we're obviously stationary on the Earth. But that was how he tried to explain it. And here's kind of like the math behind it. You have because of this ellipse, you get this sine curve. And then when you add in the tilt, you get this one here. And when you combine them together, this is the equation of time here. And that's basically what they call the equation of time. So another thing that makes it kind of like once you like get your head around understanding that, then you learn something else. So this was taken in the southern hemisphere in Australia, and you'll notice that the smaller part of the loop is upside down. This is actually not the right direction, it's more like this when they look at it. But those smaller loops upside down. So at the equator, the loop, the figure 8, is going to be exactly sideways. And at the North Pole, the loop is going to be at the top, and it's going to be straight up and down. And at the South Pole, the loop, the small part, is going to be on the bottom.
So that could be, it could look like a South Pole image, right?
Yeah, so this one would actually be what it looks like at the South Pole, except at the South Pole you can't see the entire thing because there's 6 months of night. So then basically the rest, I just have a bunch of pictures. There's not actually a lot of pictures out there.
You get what this picture is? Good. I think it's complicated.
Yeah, there's not a lot of pictures out there on the internet, so I basically got all of these off of APOD, Astronomy Picture of the Day. And so based off of this, you can kind of like, if you couldn't see this part, you could tell where on Earth this was taken based on the angle, like, because I explained how it's like sideways at the equator. So here's, the same guy took all these ones around Greece.
Do you know who it was?
I could find that information.
So that one picture takes 365 days to take.
Yeah,
Mhm.
yeah. That's probably why there's not a lot of
Be dedicated to be in that spot every single day of the year. to take
Yeah.
a
At
picture.
that
Yeah,
time.
he set up a camera and took an image of the sun every day at noon.
That's dedication.
Yeah,
That's
and
What an excuse to live in Greece, heck yeah.
great. Based on the dream.
so here's the Ukraine. So there's actually kind of like based on this, I thought that like some of these might not even be true on where they say they were taken because the angles were different. And just because they're pointed like some are pointed that way and some are pointed that way, I think the picture is just flipped. It's not actually different. So there's Hungary. So this guy just took it from his like front yard. So I guess that was a lot easier than walking up this.
Did you ever notice that in the sky, like when you look at the sun? You can't tell just by watching the sun with
You
your
have to take it the
eyeballs.
exact same time
Can't
of day
fix-
too, right?
Like this
Take
one,
it at noon every
this
day.
supposedly was taken
Yeah,
in the
you could do
Middle
that.
East,
Take a picture of the sun every
but the
day.
Middle East is on the equator.
That's
So I don't know why half of it's below the horizon. So that was
They
like,
picked a bad time to do it.
the cool thing about
It's-
this one,
It's not noon.
this guy did a lot of planning though. This little tiny black dot, that was the day
The
that
transit.
Venus transited across the sun.
So he scheduled his Analemma series to be when the transit would be at its up there, so he took it at that time of day,
Yeah.
which was obviously kind of late afternoon.
Yeah, so that's like a lot of planning to get it the same time of day.
Well, maybe he took it at 4 o'clock every day instead of noon.
And this one, the guy planned it for an eclipse. So that one is actually a lunar eclipse. So like that's probably why this guy's is like in the evening, because he had to do it every single, in the evening every single time.
That's the sun?
Yeah, that's the sun.
Okay.
This is an analemma of the moon. So this is over the course of a month. And this was taken in New Mexico. So that takes some planning too. But the moon, because the moon is actually, like here's the Earth, because the moon orbits like this, it kind of mimics the same reason we have the tilt. And also because the moon's got an elliptical orbit, it makes the same kind of figure 8 pattern, which is pretty neat.
Go figure.
Here's on Mars.
Now, this is cool. So why would it be so different on Mars?
Is our axis slightly different?
It's because of Mars's axis and the shape of Mars's orbit, right? You go ahead, Aaron, I'm sorry.
And
but-
so like, and based off of what I learned here, it's kind of neat because I looked at this, where this this was the polar, what was it, the polar lander?
Is that Phoenix?
Or not the polar lander, the Polaris? I don't remember,
Voyager?
but this was
Pathfinder.
landed on Pathfinder.
Pathfinder.
It was on the equator, and since we know that on the equator it's like sideways, this is pretty much basically sideways, so that makes sense. And the reason it doesn't have the rest of the analemma here is because like Mars orbit, like say Earth's orbit's like this, Mars orbit's even more like
More elliptical.
more elliptical. So it cuts off. So there is like an invisible tiny loop here, but it doesn't really show up. Yeah, so
pretty
that's
amazing.
that was it.
Nice. Questions?
Anybody have any questions about this?
That's pretty sweet.
Wait, so,
So if anybody wants to take a picture of the sun every day for a year for extra credit,
on
he
the,
suggested it.
at the North Pole,
Uh-huh.
would the Analemma be at the shorter side?
At the North Pole, it'll look exactly like this, straight up and down with a little loop on top. But because there's 6 months of night, you won't see this part. So it'll just like look like that, and the horizon's like that.
So the South Pole would be the opposite?
Right. The South Pole, you just see the bottom of the top.
Okay.
That's pretty big.
Kinda like that.
Weird. Any other questions?
That's pretty sick.
This is something you can just kind of chew on.
If you want to, it's really interesting to try to think about it if you want to get into something.
Another question?
What does the degree of rotation mean? Like, what
That means where on Earth you are. So like if you're at the equator, it's going to be exactly sideways. And as you move south, this lower loop moves up. So like it'll be like that,
It's about the latitude.
and it'll be like that, and it'll be like that, and then it'll be like that. Oh no, like this was the Earth, the South Pole. That.
Oh, yeah, that's big.
So like here's the equator. Which is like, after I learned all this stuff about this, then when I learned that, I'm like, what?
Any other questions?
Do you know why they call it that name?
I
That's a
do
good
not.
question.
That's a good question.
Sounds kind of Greek,
Yeah.
doesn't it?
Yeah.
What's Azerbaijan?
Yeah. Oh, you mean the analemma or the edge or?
I meant both.